Okay, so let's do a full derivation of the equations that we got for charging a capacitor. Okay, so at t equals 0, this capacitor is uncharged, and I'm going to close the switch, okay? And that's going to charge the capacitor, right? So current will flow from the battery to the capacitor, and then charge is going to start building up on the capacitor. All right, so let's see, analyze this a little bit better, thinking really about what are the, if I attached a voltmeter across this resistor, and if I attached a voltmeter across this capacitor, what am I going to see coming out of here? So we know that the voltage across the resistor is the current through that resistor times the resistance. And we know that the voltage across the capacitor is the amount of charge on each plate divided by the capacitance. So as the charge is flowing, this Q is building up, right? So that voltage is going to be going up, and because they have to add up, and with the loop rule, then the voltage across the resistor is going to go down, so that the current is going to go down. Okay, that's just sort of where our brain's going. Let's make sure to write down that loop rule. So we go plus E, so we're going to start here, and then go that way. And then we're going to have a voltage drop down the resistor, and then we're going to have a voltage drop across the capacitor. And in case you're wondering, sort of, is that a drop? Is that a raise? I'll remind you that the positive plate of the capacitor is going to be there, the negative plate is going to be there, so you're going from a higher potential to a lower potential, so that is in fact a drop. So our signs are correct. Fantastic. All right, so I wonder if I could get an equation for the charge on the capacitor as a function of time. And that's my goal here. Well, I can first start by remembering that current is dq dt. So I'm just going to rearrange this real quick. I'm going to bring the negative guys over to the other side, and I'm going to rewrite our current as dq dt. Okay, so what this is a differential equation. And the way to solve differential equations is that there are general solutions, and then we're going to put our initial conditions in to figure out what that particular solution for our equation is going to be. Okay, we can do sort of one more thing. And this way you can kind of see how this RC comes out, and then that E over R, the EMF over R probably looks to you like a current, so hopefully it does. But the general solution is of the form A times e to the negative beta t plus b, something like that. So the way to solve differential equations is you have this general solution, you take a derivative, you plug it in, and then things pop out. I do not think it is worth any of our times to watch me do such a thing, but I will give you what you end up with. You get C times the EMF, 1 minus e to the negative t over RC. Okay, so let's make sure this has the right pattern. So what was Q of 0? Q of 0 should be 0. Let's check it. 1 minus e to the 0, that's 1. So good. 1 minus 1 is 0. So fantastic. Okay, so what is it when t goes to infinity, right? So this is our steady state solution. This is our after a long time, right? These charges are just building up on this capacitor plate. This voltage is getting bigger and bigger and bigger, and this voltage is getting smaller and smaller and smaller. And so we're looking at the charge after a long time. And then, of course, that's 1 minus e to the negative infinity. That's 0. So that's our charge after a long time. So that's what we were talking about before, calling sort of Q max. Sometimes it's called Q naught, right? But what is this, right? This is the voltage of the battery, right? So when we say Q equals CV, this, right, that's the voltage across the capacitor, and that's the thing that keeps getting bigger and bigger and bigger as the charge gets bigger and bigger. And it gets so big that the current stops, and this voltage and this voltage are the same. And this, of course, is it's an asymptote situation. It's not it doesn't actually reach there. Okay, so this Q versus T, that value that it goes to asymptotically is that Q naught, which is C times the EMF of the battery. Okay, this is the exact same graph for V sub C. Because V sub C is proportional to Q, they're going to have the exact same shape, and that value that it's going to asymptotically reach is the EMF, right? So we can actually, so we have a Q of T in a box right here. We also can write the voltage across the capacitor as a function of time, which is, of course, Q as a function of time divided by C. Well, that was CE, 1 minus e to the negative t over RC, and that's divided by C. So you see this exact same form. I'll just smack that over there. You see that exact same form of equation. And again, that thing in front is the value of your asymptote. And that's VC. And, oh, sorry, we had Q of T. So I'll write this again. Q of T is CE. And again, when I say E, I'm talking about the EMF. If you want to write like V battery, that's totally fine. So if we have that function, let me just move that stuff up here. What is I of T, right? What is that current that's going through the circuit? Well, that's dQ dt, isn't it? Okay, so ddt of CE minus CE e to the negative t over c. Okay, so that first term is 0. Now we have negative CE, and then we are going to we're going to keep that e to the negative t over RC, and what's going to come down? 1 over, oopsies, negative 1 over RC, right? It's that guy. Cool, so let's simplify that. So we got our negatives go away, we get a little positive, and our C's go away. Ooh, cute, right? Those positive guys. So what is that? Oh my goodness. So that hopefully should look familiar. So this is I of T, and that maximum value, that's our I max, or sometimes called I naught, right? And that's E AMF over R, and then that is a decaying exponential, but it still has that e to the negative t over RC thing. So all that, so in both of these situations, this time constant of RC tells you how fast how fast something is growing or decaying, right? So that the time scale over which that happens. Okay. So if you have a bigger resistor, then it's going to take a longer time for these decays or growths to happen, and same thing with capacitor. If that's bigger, it'll take a longer time to charge or discharge, however that's going to happen. So if this is the current, then there's one other graph that you might be interested in, and that's VR, the voltage across the resistor, which of course is proportional to, sorry, these are of course are by time, which of course proportional to the current. And then that maximum voltage is going to be that, that EMF. Because when you first start this thing charging up, this looks like a wire, right? When Q equals 0, this looks like a wire, and so the current going through here is just E over that R, that initial current. Okay, hopefully that helps. Just want to show you one last thing. We started this whole process by saying that EMF of the battery had to be equal to the voltage across the resistor plus the voltage across the capacitor. Let's just make sure that that is true at all times t. So VR is the EMF, that guy, and VC is the EMF, that guy. Well, looky there. Boom, boom, boom. Check.